All right, I think we start. Welcome to this week Autonomy Talks. This week is a great pleasure to have Dr. Carlo Cenedese, who is a postdoctoral researcher at ETH Zurich, working in a group of Professor John Liggeros. Something about Carlo. Carlo obtained both his bachelor's and master's degrees from the University of Padua. He then moved to the Netherlands, where he obtained his PhD at the University of Groningen with the PhD thesis titled Multi-Agent Network Games with Applications in Smart Electric Mobility. And he then moved to Zurich. His research interests include both theory, including game theory and distributed optimization, and applications, which include incentive-based traffic control and smart charging of electric vehicles. Specifically, in Professor Liggero's group, he works on incentives to ease congestion on electricity and road networks. Today is going to talk about highway traffic control via smart e-mobility, and we are very excited to hear what he's going to talk about. So go ahead, Carlo, the stage is yours.
Okay, thank you very much, Joelle, for the nice introduction. And thank you all for being here, even though summer is kicking in. So today I'm going to talk to you indeed about highway traffic control via smart mobility and what we mean by this title. So first of all, I want to start by thanking my co-author, that are Professor Michele Cucuzzella, Professor Sergio Grammatico, Professor Jacqueline Skerpen, and Professor Ming Cao from the University of Groningen. Now, with the growing urbanization of the nowadays cities, you can see that the increment in people in the urban areas create also an increment in the congestion, as it is natural to assume. And this, on top of creating some discomfort to the commuters, create also huge losses in terms of monetary ways. So it is a big problem that has to be faced in nowadays society. And on top of this, not only we have a problem from a monetary point of view, but also a high level of traffic congestion creates an increment in CO2 emission. And as you can see here on the graph on the right, this increment arises both when there is a very low velocity at which people travels and when there is a very high one. So traffic control usually split in two categories. You have speed management, when you want to handle the case in which people are speeding, and congestion mitigation, in the case in which you want to mitigate congestion, therefore increasing the overall velocity at which people travel. And we are focusing on this latter one. And in particular, I want to first have a little bit of an overview of some of the possible traffic control policies that can be put in place or are quite common nowadays. So one of the easiest one that everybody can imagine is traffic lights. That basically tells you when you can or cannot travel. There's a huge impact because people are obliged to comply to such a policy. But the control frequency that you can implement and the dynamicity of the control action is not that high. Similarly, you can have tolls or also the price of the road on which you're traveling, in the case in which you're considering a highway, for example, or even the speed limit. In all these first cases, these purple cases that you can see here in the table, we are implementing some hard measures. Hard measures means that we are decreasing the user choices. So we are basically obliging the people to comply to a rule that is there, otherwise there will be consequences. For example, there can be some fees, or they just simply cannot go through the road if they don't pay such a price. In all these cases, therefore, we are going to limit the user's choices. There are other type of policies that can be put in place in order to achieve a relief of the traffic congestion. And this can be based on incentive. And for example, there can be a time incentive you can imagine, for example, a Google Maps that tells you in real time if a road is faster than the one that you are currently doing, because in front of you there is a congestion. Therefore, it will give you an incentive to deviate from a congested road by means of a faster one. And by this approach, they basically achieve a double solution. First, you make the user happy because he will travel via a faster road, and also you will have that the congestion decreases. Another one is monetary incentive, that is somehow the dual of increasing the price of a road. So instead of in this case, if a user chooses a road that is not congested or travels through a highway, let's say outside of the rushing hour, you are going to give them an incentive in terms of money to basically incentivize such a beneficial behavior for everybody. In such a way, users are, as you can see here, are nudged toward the behavior that the operator of the road is interested into. They are not obliged to comply. So in this talk, I'm interested into leveraging such a later policy. So we want to design a soft policy that leverages the charging of plug-in electric vehicles. And we want to do so by means of a dynamic energy price. How do we do that? Well, as I said, we want to link traffic congestion and energy price. Therefore, the price of the energy that the electric vehicles purchase decreases with respect to the level of traffic congestion. When the congestion increases, there is a discount on the energy price. Therefore, what you obtain is that if you have some drivers that are interested into maximizing their profit from this discount and minimizing their travel time, there will be a trade-off, and there will be a congestion relief that is an emerging behavior from such a selfish action of the agents. Now, why do we think this will work? Well, the characteristic of this control strategy is, as I said before, being a soft policy, having an impact that is scalable with respect to the increment of the electric vehicles on the road. Therefore, ideally, it will be incrementally effective during the next years, and it will be highly dynamic because we will change the energy price with respect to the current situation on the road. And what does this policy leverages? It leverages the travel time, because the idea is that if there is a traffic congestion in front of you and you are going to spend 20 minutes charging, those 20 minutes are the same one that you would have spent inside the congestion. So it's not that you are increasing your total travel time by a huge amount, but at the same time, in those situations, you are gaining money. Then the discount on the energy price, so a monetary incentive, and also a psychological factor that is called range anxiety that the drivers of electric vehicles usually exhibit. That is the fact that even though the battery is not actually empty, or doesn't need really to be charged in order to completely fulfill the journey, well, they will charge it anyhow, because they have this anxiety of not having enough energy. Okay, so this is how my talk is structured. There I will go through the cell transmission model, that is the traffic model that we use. And I will describe a little bit in detail the decision-making process, the control scheme, and then I will go through the simulation that we have done using some real data extracted from the highway in the Netherlands. Let's go through the first one, the CTL model. So the cell transmission model is a traffic model that describes the flow of vehicles through an highway. We assume that there is only one charging station in this case. And then we assume that it is divided in L different cells. So this is how we model the overall flow of vehicles. Then you have yes, the CTM describe the flows. And inside each one of these cells, over here, you will have that vehicles move at a constant speed. And each cell is connected to the one after through an interface over here, okay? Now, here are the main variables. We are going to consider the traffic density that is inside a single cell, the in and out flow, and then this phi here is the flow that flows from one cell to the one after it. And the two main variables that we introduce in this work are the road to station flow and station to road flow. Basically, are the flow that from cell one goes into the charging station, and that from the charging station goes to cell two. Okay. Now, the cell density is very simple, and it's just basically an integrator. And here you have that the phi plus is the inflow, and phi minus is the outflow. Therefore, at every instant in time k, the CTM is completely defined, except for these two variables, R2S and S2R, because these are defined by the decision-making process in which the electric vehicles are involved. Because the whole rest of the model is basically a free evolution of the input over here. Okay, so what we are going to do next is to describe the decision-making process that the vehicles that are going to exit cell one faces in order to decide whether it is or not convenient to stop at the charging station. And this is exactly what we're going to do next. So the decision-making process. Let's first focus on the cost. So on the objective of each one of these vehicles. Well, we consider first a couple of quantities. PEV is the percentage of electric vehicles that are on the road. This calligraphic E is the set of electric vehicles. And this calligraphic T is the prediction horizon over which the vehicle decide whether it is convenient or not for them to stop at the charging station. So each driver aims at minimize its cost. And as I said before, it is a combination of a cost due to the time, so the travel time to arrive at their destination, and one that is due instead of the price of the electricity. Okay, so how much they can gain out of the discount. So these are the two parts, the cost that each driver wants to minimize. So let's try to go through each one of it. You have the first part that is associated with time. We define by this exceed additional travel time due to traffic congestion. And unfortunately, we cannot have a real definition of this over the future instant. Therefore, we create an overestimation of it in the worst case scenario, and we obtain such a formula over here. We obtain a recursive formula in which basically you compute the difference between the travel time in free flow, that is this part here, and the travel time through cell L in the actual worst case scenario, okay? And in such a way, you compute the additional travel time due to traffic congestion. Now that we have this component, we can have another part, C, that is the additional travel time due to those electric vehicles that are exiting the charging station close to the time in which an agent I is exiting the charging station too. So if Ti is the time at which agent I enters cell 2, therefore either exit cell 1 and enter directly in cell 2 or exit the charging station, then we can use a binary variable theta that takes value 1 when T is in the neighborhood of this Ti and 0 otherwise, and compute this additional travel time in such a way. Basically, you just have all the PAV that exit in the neighborhood of Ti takes value 1, and the others takes value 0. These are the electric vehicles that already took their decision, so they are not involved in the current decision-making process. And this one are instead those vehicles that are indeed involved in the current decision. And this is why there is this double summation. So this is all this weird formula does. Therefore, we're ready to describe the total cost due to traffic congestion. So associated to the extra time that you will spend due to traffic congestion. And it is composed of this part. You will have this component here, T minus K, that describe the time that a vehicle actually spends at the charging station. You can see that if a vehicle decides not to stop, therefore he will choose T equal to K. This part is equal to 0. Therefore, he will experience only these 2 additional extra travel time due to the traffic congestion, and here instead the one due to the vehicle that are exiting close to T, that in this case is equal to K. And then we have this one that is a normalizing factor. And this value over here that is theta I instead is the binary variable that basically select only that takes value equal to 1 only close to Ti and 0 in all other cases. Therefore, out of all these values, we select only those, we sum over only those that are close to T1, okay? Now, let's go to the second part of the cost that is associated to the price. The price is designed by an entity that we call the highway operator that broadcasts this price to all the electric vehicles. And the vehicles actually decide whether it is convenient or not to stop based on such a price. This price is designed basing in this way. So it is basically a combination of the base energy demand of the grid. So the demand that is not associated with electric vehicles, it can be house or companies or whatever else. Then you have UPV, so it is the total energy purchased by the electric vehicles at the charging station. And this delta over here, that is the actual additional travel time that is currently in the highway. So as you can see here, there is a minus, so there is a discount associated to the level of congestion on the remainder of the highway. So as you can see here, you sum from 2 to n that are the remainder cells. Now, also in this case, unfortunately, we cannot compute this additional travel time in the future time instant because we don't know what the vehicles that are behind the current one will decide to do, whether they will stop or not. Therefore, we do this estimation of this delta hat in the worst case. And we obtain a formulation that is an approximation of the price that is actually the one that is broadcasted to the electric vehicles and over which and that the electric vehicles uses. And it is basically so we basically use these 2 variables, beta 0 and beta 1, in order to make this p hat very close to the actual price that will be actually implemented afterwards. That takes the formulation before. Now, as I said, we have so we can define the energy purchased by the electric vehicles I with UI, and now we are ready to describe the cost associated to the price. That is very simply the amount of energy purchased by the price at which the agent purchases it. And it is the difference between P bar, that is the actual price that he would face if he does not charge at the charging station, and P hat, that is the estimation. This quantity is equal to 0 in the case in which there is no congestion at all on the road, because this P hat would be exactly the same. So because of this P bar, because there would be no discount at all. Okay, so in that case, the vehicle will not have any incentive, and therefore he will not stop unless he really needs to. So the final formulation, as I said before, looks something like this, where this alpha here basically describe how much a single agent is keen to be influenced by the variation in price or in time. It can be individual for each one of the electric vehicle involved. Okay, so there is quite some flexibility in this formulation. Next, we have to describe the state of charge dynamics, so how the battery charges, and we use a very simple integrator. And we use another binary variable that models whether the electric vehicles are charging or not at the charging station. And you will see, as you will see, we are going to use several binary variables because we want to be as close as possible to the real case. So we want to model several phenomena that can happen in the charging station and in the charging and discharging of the electric vehicles. So next, what we do to fulfill this this goal of modeling in the best way possible this problem is to impose some local and coupling constraint. And we do that by imposing a collection of logical implication, such the one that you see above here. And we describe the following. First of all, we impose that the variable theta takes this form. So it has this sort of rectangular shape that is the one that I told you before. So it takes 0 value everywhere except in the neighborhood of Ti, that is the time at which vehicle I decided to enter cell 2. Then we impose that the electric vehicles that merge in the mainstream merge immediately in the mainstream if they are not charging. That if an electric vehicle stops to charge, then it has to exit the charging station. And also the fact that if an electric vehicle decided to charge, then it has to charge for at least h bar time instant. And if it is decided to stop at the charging station, it has to stop for at least a certain amount of time instant. So it cannot enter and exit immediately or something like this. So we want to avoid this sort of unnatural behavior. And for each one of these, basically, we had to implement some logical implication by means of some binary variables, some integer variable. And that's why later on we're going to use mixed integer games. Then we also have some coupling constraint over the decision, and these are associated to the total energy purchased by the electric vehicles. So we want that is strictly smaller than the grid capacity, so it doesn't exceed that. And also the fact that the number of electric vehicles that are charging at the same time is lower than the number of available plugs at the charging station. Now, how we do formalize all this decision-making process? Well, we formalize it as a non-cooperative game, G, in such a way. So all agent I want to minimize the cost function subject to the local and coupling constraint. Okay. Now, this constraint, as I said, are logical constraint, but we are able to linearize them, basically to transform them in equivalent linear inequalities by adding auxiliary variables. Therefore, we can translate this game in a more well-known formulation of a game in which you only have this linear inequality, so basically a fine constraint. And the Z is the vector of all the decision variable for an electric vehicle I, and the Z minus I is instead all the variable for all the decision variable of all the others. And this K over here describes the fact that it is the decision-making process that takes place at time instant K, and at time instant K plus 1, there will be a new decision-making process with new vehicles, okay? So this is why there is this index K over here. Next, we can prove that G is an exact mixed integer potential game. And we are interested in studying whether or not such a game will reach an equilibrium. So we will reach a collective strategy Z. So this Z describes basically the charging schedule of all the electric vehicles, such that no unilateral deviation from it will create a decrement of the cost function of one agent. Well, this is the question, and what we implement to achieve such an equilibrium is an iterative sequential best response. And we prove that such an algorithm based on this update rule ensure global convergence to an epsilon mixed integer Nash equilibrium. Okay. So the IO operator takes care of the communication among PIV. As I said, basically what it does is to collect the information of the current strategy of the agent and decide the price, and then broadcast the price once again to the agent. And since the update is sequential, there is only one agent at a time that is updating its strategy. Now let's see a little bit a schematic description of how this algorithm works. Basically, from the real world, there is a communication to the highway operator of the current traffic data. So, for example, the travel time and the density over the cells. Then the highway operator uses the cell transmission model basically as an oracle to obtain all the quantity he needs to compute the price over the prediction horizon. And then the game starts. So the highway operator broadcasts to all the agent this p hat plus some aggregated variables used by the agent that is performing the update to decide whether or not he has to change his strategy. And then this agent sends back the new strategy ZI to the highway operator. Therefore, there is this exchange among highway operator and agent of a single strategy, and the highway operator send aggregative values to the agent. And this algorithm is iterated until we reach an epsilon mixed integer Nash equilibrium of the game. And this is basically the optimal schedule, optimal charging schedule for the electric vehicles. And this is exactly what describe the true flow that I talked to you at the beginning. So the decision of the optimal charging schedule, so whether the vehicles decide to stop or not, and for how long they want to stop or not, and for how long they want to charge also, describe and define these true flows. So the flow from the station to the road and from the road to the station at time k, okay? And therefore, this goes back to the real world, and there you go to the instant k+1, and you start to and you start a new decision-making process. So this describes more or less the algorithm. Now, since we have done all this theoretical work, now we want to go through some simulations. And in particular, we are going to use some real data that we extracted from the A13 highway in the Netherlands. That is the highway that connects the Hague and Rotterdam. And we consider 8 sensors that are spread apart more or less evenly, around 500 meters from one another. And it is obtained by NDW portal. You have this sensor from S1 to S8 that basically measure the flow of vehicle in the interfaces among cells. So from this data, you can extract the data, compute this graph that is called fundamental diagram, and use the actual identification of this graph to identify indeed the CTM, so all the variables associated to each one of these cells. So this is what we have done. And then we simulate the presence of a charging station and see how the travel time over how the travel time will change with the presence of such a charging station or not. So delta 0 here is the travel time in the case in which there is no charging station at all. So as you can see here is the highest one. And the others instead are the travel time in the case in which the electric vehicles is the 5% of the total vehicles on the street, 15 and 25%. So we wanted to go a little bit to a stretch, if you might, because 25% is a lot, 5% is instead more or less realistic to the actual level that are right now on the street of electric vehicles. And as you can see, the behavior is quite interesting, and it's remarkable because we can achieve this basically peak shaving, this peak shaving of the traffic, of the travel time. So there is a huge decrement, especially of this big peak in travel time in the afternoon, and all the others instead still are better with our approach instead of without. Now let's see a little bit more in detail. You can see that in the morning we have a smaller rush hour, so we have only 1 hour, more or less from 7:45 to 8:45. In the afternoon instead we have a very big congestion time that lasts more than 2 hours. And in the morning you can see that we are doing always better, because in this case we are plotting the difference between the original one, travel time, and the one with our approach, so with the presence of the charging station and the soft policy based on the price of the energy. And as you can see, we are doing always better. We are doing even better the more vehicles are present. Here instead is a little bit more tricky, because since the congestion is so wide, basically what happens with our approach is that you are spreading the vehicles throughout the whole congestion, because the congestion is so big that you cannot simply completely so to have zero congestion at all. But what you can do is to decrease the peaks, as in this case, for example, and distribute again over here and here the vehicles. So you are incentivizing people to stop when there are peaks and to merge back into the mainstream when there are lower peaks. In this case, you had to do this sort of ballet feeling effect you have, because it's just too big the congestion that you face in the afternoon in this case. And then we're going to define this performance index, that is basically the summation over the whole time of the difference between the prediction, between the travel time without and with the charging station. And the bigger the better of this index. We are going to use it after for the next simulations. Now here we can see the plots of the station to road and road to station flows. As you can see here, in the morning you have quite some vehicle that stops. Then the vehicle do not stop at all, because as I said before, if there is no congestion, there will be no incentive. Therefore, it is just a waste of time for them to stop at the charging station. And then they start again to stop over here. As you can see, during the highest peak, there is the highest amount of people that actually stop at the charging station. And then it decreases immediately after, okay? Next, a very important thing, a very important feature of our algorithm is that it provides always satisfaction of the hard constraints. So it doesn't matter at which point you stop. So before there was that epsilon that is basically an approximation of the optimality that you can pick as close to zero as you want. But if you pick it higher, obviously the number of iterations you need to converge will be lower. But it doesn't matter how big you choose it, the constraint will be always satisfied. So you will never, for example, go over the maximum grid capacity that you can see here in red, but you will lose something in the optimality of the solution. So maybe the solution is not the optimal one for the agent, but at least is a safe solution. So we wanted to basically emphasize this aspect. Next, we can see basically the difference between what happens if you increase the number of plugs available at the charging station and you increase the incentive. So the higher the incentive, as you can expect, the better is the result of the policy. So it is interesting, this graph, because you can see that there are some level of incentive that basically produce almost no result at all. So you have to have at least 5% of incentive in this configuration to achieve some satisfactory result. And then it is also interesting to see that the higher incentive in this case, the higher the performance. So there will not be a case in which the performance are lower in the case in which if you increase the incentive. And then it is also nice, interesting to notice this big leap that happens here in terms of performances. And this leap over here is may suggest that it is not always linear, the effect of a higher number of charging spot with the performance that you achieve. So you have to be careful to whether or not it is beneficial or not to increase the number of charging spots. Next, I want to show you a couple of other graphs that consider the variation of different quantities in the overall problem. So the first one that you can see here on the left is an increment in the heterogeneity of the users. So the value of alpha over here is pretty much homogeneous, and over here is quite diverse among the users. And it is interesting because it seems that there is an almost linear increment in performance with the more the agents are heterogeneous. So the more they are diverse one another, so the more they value differently the time and the price, the higher the performance. And this makes sense because it might create a more efficient use of the charging station, because if everybody wants to take the same decision, well, at that point, everybody will try to go for the same charging schedule, so they can create some congestion at the charging station. Okay, so this is why an increment in heterogeneity will create an increment in the performance. Then another one that I think it is interesting is how the increment of a charging spot, delta bar here, grows, how the performance grows with respect to the percentage of electric vehicles. So if you have 5% of electric vehicles, you can see that here you will experience a sort of plateau, and therefore there will be no reason to increase the number of charging spots. Probably it would be more beneficial to create a totally new charging station farther along the road. But if instead the percentage of electric vehicles increases, this basically saturation point of the performance is way farther down the road, so you can increase the charging spot and achieve better performances. So this is also interesting because an analysis done in such a way, so by modeling carefully the problem, allows you to study how this variation of the parameters affect the performance. So somehow we'll give you some hint on which one are the policies that make more sense and we have a better effect over the traffic congestion. And this is one of the main results of our work, and we think that is one of the most valuable. Finally, another interesting graph is this one. So we plot here the percent of incentive. So here you increase the percent of incentive, and here you increase the percentage of electric vehicles. You can see here that the performance increases. So the optimum performance, you will have it at 15% of incentive for a percentage of electric vehicles that is 5% and 10%. And then at 35, when you have 15% of electric vehicles and 20% of electric vehicles. But it is a little bit strange because basically tells you that you don't have to give the highest incentive ever to achieve the maximum performance, and it is counterintuitive. But if you go and watch at the graph, what you will see is that if you increase even more the incentive, everybody is willing to stop. So even when people do not experience a dramatic traffic congestion, so they are not very close to a peak, they will basically stop and create a congestion, and therefore the vehicles that are actually close to a peak will not stop, and therefore you will not have that relief of that peak, because all the charging plugs are occupied by the others. In order to, and this is mainly due to the fact that the afternoon peak is way longer, and therefore you can have this sort of phenomena. So what we have tried to do is to create a dynamic discount. So not a discount that is fixed over the whole horizon, but that varies. And we have seen that if you apply a higher discount during the morning and a lower one during the afternoon, you mitigate this effect, and therefore you achieve what you would, well, first of all, way higher performances, but at the same time, you achieve what you would expect, that higher incentive create higher performances. Okay, so this is what we did. So to conclude, in this talk, I presented a novel active traffic demand management based on soft policies, and we link together the traffic congestion and the energy price for charging of electric vehicles. We formalized the overall problem as a non-cooperative mixed integer potential game, and proved that under a sequential myopic best response, such a algorithm converges to an epsilon mixed integer Nash equilibrium of the game. Now we implement a semi-decentralized control structure that is based on the broadcast of the energy price from the highway operator to all the vehicles involved in the decision-making process. And finally, we validate the benefit of such an approach with real-world data. And this simulation, we have also done a sensitivity analysis that can suggest which one can be the intervention that can be more beneficial or not to implement such an approach in the real world. So thank you very much for your attention. And if you have any question, I'm here to answer. And I want to thank once again my co-author.
Thank you, Carlo, for the talk. Are there any questions from the audience? Maybe to break the ice, I have a couple. So I'm quite curious about the real world case studies you did. In particular, you mentioned you took real data. I want to understand what's the demand for your model. So you assume current cars driving on the specific highway you're looking at, or did you assume certain plans for citizens that move around? It was not clear to me if you were assuming that people were on the highway and they had to charge at some point and simply to schedule when they had to charge, or you were taking into account the plans that the actual citizens.
Okay, so what we did is to extract the data about how people are actually traveling through that highway, okay, during a normal day, and then assume that there is a certain percentage of electric vehicles, so 5%, 15%, 10%, something like this. And among them, we provide them with some goals. So each one of them will have a certain percentage of batteries. And then you will have that they have a certain interest into saving time or saving money. And then basically what you have is that they will decide based on that. So if somebody has a very, very low state of charge, then he will stop at the charging station because he needs that to complete his journey. But the others, on the other hand, they will basically decide based on convenience. So this is the main idea, let's say.
Okay, then what I was wondering is, do you think it's possible to include constraints on the plans that the citizens have? Here, you're not assuming autonomous vehicles, so I imagine you're driving your car to work.
Yes.
You're not completely free in your choices, right? At some point, you have to get to work. These kind of constraints, can they be included in your model?
Yes, you can put some constraint over the, for example, maximum travel time or yes, let's say in this case we consider a highway without exiting, so we did not consider a network streets, so you cannot basically change the street in which you are traveling. But you can definitely use a similar approach and put some constraint over indeed, for example, the time of arrival, the maximum time of arrival, or something like that.
Okay, interesting. I have maybe a second one, which is, I imagine there are some differences, but so you looked at this specific highway. So I imagine it's a network in which you have a road arc, or maybe two parallel ones, one going back and forth. What about if you consider a city? Does, for instance, your congestion approximation method or other things not scale well if you suddenly consider a grid-like network that could be a city center?
Yes. So with a city, it would be more tricky. This is something that we're working on, because this approach is basically a microscopic approach. So we try to model every single decision of every agent. Okay. It is true that it's a semi-decentralized approach. So the power of computation is on the vehicle. So it's not a centralized approach in which you have to compute the solution for each one in a centralized fashion. But first of all, you have to use different tools. It might be the macroscopic fundamental diagram, the one that you have to use, that is instead of the fundamental diagram to describe basically how the flow will vary among different areas of the city. So in that case, you might consider area of a neighborhood of the whole city instead of considering just a highway. But I think that a more natural approach in that case would be to model more of a aggregated flow. So basically you are going to describe as an aggregative approach how the flow will be split among different roads instead of considering the single decision of one agent. But at that point, you will lose a little bit the information over the single policies, how it is structured, and how all the constraint plays a role. So I think it's a little bit of a trade-off between the problem that you want to solve.
All right, yeah. So I guess that's one extremum, and the other could be, the way in between could be to have connected highways, right? So
yes,
that could
if
be,
you have something, yes, indeed, something that we are working on, and we would like to study, is the case in which you have like a ring around the city. So, for example, if you place several charging stations, which is the best charging position? How many charging spots should there be to have an efficient traffic congestion alleviation? Or maybe even because in that way it will be quite interesting to study such a problem, and it is quite confined that you can still use a microscopic, let's say, approach, I would say.
That's interesting. Thank you.
Thanks.
Are there other questions?
I have a question.
Go ahead, that's it.
Thank you, Carlo, for the nice talk. My question is in regards to the heterogeneity of the agents.
Yes.
So you mentioned that they are heterogeneous in their alpha parameter. They can be heterogeneous in their alpha parameter, but there is also some heterogeneity in time for the single agent based on their charging state. Is that right? So like,
what do you mean? Yes, there is heterogeneity in the level of charge of the battery, because they will have different state of charge, different agents. So they will take a decision based on that. What we did to estimate this value over here, so to make it basically a sensitivity analysis, is to fix the state of charge for all the vehicles and make only alpha values. But it's only for this particular graph that you can see here on the left. Because we wanted indeed to estimate how the preference between time and monetary incentive plays a role. But in the rest of the work, yes, you are right. There is several places in which the individuality of the agent plays a role. One is this preference, one is the initial condition that they face.
Okay, and how do you draw that initial condition?
So since we have so many vehicles, what we did is to assume that almost all of them, so a very high percentage, like 97, if I remember correctly, percent, has a state of charge level that allows them to arrive at their desired destination. Because since we are focusing on commuters, usually it makes sense that you start your journey having at least enough battery to arrive at your destination. But the rest, basically, what we did is to use a normal distribution, and what we did is consider almost all the vehicles that are on the market, where their current share over the market, so Teslas, BMW i3, and all the others, and considering the actual battery capacity, and draw a percentage of that. So we consider heterogeneity also in the particular car that they are using, and in the efficiency that they have. Okay. But it is basically a random distribution among the percentage of battery.
And did you notice anything interesting when you play around with this kind of heterogeneity?
You mean a different state of charge?
Yes.
Yes, so the less heterogeneous people are, the more you will face some sort of congestion, because their choices will become closer and closer. So in general, what we have seen is that the benefit that they can take is proportional to how long they can charge, right? Because if you have 10% of battery, you will charge 90%, okay? You will take that discount for that 90%. If you have 95% of your battery, you can only charge for a small amount of time, because after the 100%, you will not charge anymore, and you will get nothing out of this policy, right? So if you have a lot of people that have a very low state of charge, then you will have longer staying at the charging station, okay? And the other way around. And this can reflect into the factor that I said before, that it might happen that there will be a congestion in the charging station, so you have to be careful with this. If there is heterogeneity in the state of charge instead, you mitigate quite a lot this sort of effect.
Okay.
Thanks for the question.
So we have a question from Constantine. I think you have your hand up. Go ahead if you want.
Yes, thank you for the interesting talk. I was wondering about, so we we want to optimize some peak congestion or something, and we are incentivizing the actors with price. So I was wondering about any thoughts on extending this to multi-objective optimization. So there might be other objectives that we want to optimize. So one is congestion. Another one would be I don't know, the peak load of the energy production. So there might be some surge pricing of electricity depending on the rest of society, how much electricity is being consumed. You might imagine something like, what is the clearing price to utilize the charging stations optimally?
Yes.
So I want the charging stations to be 24/7 utilized. So how do I price so that I have a constant stream of customers? So I'm wondering how do we make this into a multi-objective optimization problem? How do we take multiple stakeholders into account?
Yes, so up to this point, what we did was to model the decision of the agent, so the single agent. So some of the things that you mentioned, even though they are very interesting, they are not part of the decision of the agent, because, for example, the peak over the grid, that is something that will take a role in the decision of the price, so on a higher level, rather than on the decision of the agent, right? So I think that your question is more about creating some sort of high-level optimization problem, in which you have a hierarchical structure that the highway operator decide the price in an optimal way, optimal in the sense of peak shaving or decreasing the congestion or something else, and then it will broadcast this price to the agent. That is something that we're working on, and we're focusing mostly on Stackelberg games, and in particular the case in which you have the highway operator that decide to, what we for now discuss is a structure that it is intermediate. So it is like a TSO that want to increase the...
Excuse me, what is that, a TSO?
Basically is in a grid, you have several layers. You have the grid that creates all the generated power, okay? And then there is an intermediate entity that dispatch the energy and can sell back flexibility to the grid, because the grid wants to have a almost flat demand of the energy.
Yeah. And
the objective of this middle one is to have basically to decrease these peaks of energy. So exactly what you said. And we try to do that. The big issue in this case is that so there are two approaches. One approach is to assume time separation. And some time separation means that the highway operator basically takes the decision over the price, then broadcasts it to the agent takes their decision, and the cycle goes back, okay? It is time separation. The other approach is instead is the one that is more theoretical, the case in which you have a bi-level optimization problem in which the decision of the highway operator takes as a constraint the game of the agents, okay? That is a more complex problem, but it is a more interesting one, in my opinion. The only problem is that the theoretical result that we have so far are for the case in which you only have continuous variables. Because as soon as you implement mixed integer variables, that you will have a lot of problem with the feasibility spaces and things like that. So if you can simplify the problem or use an approach that is more associated, for example, to the one that we discussed before with Joelle, so the macroscopic one, so more about the flow and the percentage of the flow, then in that case you can use such a solution that I think it's really interesting. Yes, but yes, but we are also open to discuss other things. So multi-objective optimization might also be another approach to do to pursue such a different research topic.
So the agent, the driver takes a physical decision to.
Yes, basically they will receive a prompt. The idea is that they will receive a prompt on their screen that tells you, if you stop at the next charging station for 15 minutes, you will save €5, and you will not. Your estimated travel time will increase of 2 minutes, or something like this. Do you want to book a spot?
So there is a booking.
Yes, the idea is that because otherwise you will not be able to rely on their decision. So the big problem with this is that, and it is a big question that is researched also in our group, is that this is basically a dynamic game with a rolling horizon, right? With a different agent all the time. And that is something that is somehow like an NPC-like structure, but with games.
Excuse me, and
like a model predictive control structure, okay. But with games, right? And that is something that is a big question, and there are not really big results right now to show the convergence to an optimum of the overall, so over the whole day, because what we have shown is the optimum of the single decision-making process and optimal for the agent. If you want instead to focus,
I was thinking in terms of a bidding situation. So the decision is not to take it or leave it decision 0 or 1, but make it into an auction game. So and basically
Yeah.
play with the parameters of the auction, like in mechanism design theory.
Yes, that works. I think that will work, and that is interesting. But still, you will have that at every instant you will have different players that plays, so they are not the same. So and then you have to obtain some claim of optimality over all the games on a row, right? So it is not straightforward because you will have this dynamic process of gaming, right? So this is something that we're working on. If you have a nice idea, I'm more than happy to have a meeting or discuss something.
I only have questions. I don't have ideas.
That's already something.
Sorry. Okay, thank you. Thank you for your time.
Yeah, you're welcome. Thanks for the question.
All right. Thank you very much all for the discussion. Thank you, Carlo, for the great talk. I think you gave your coordinates in case people want to reach out for deeper discussions.
Sure. You can just send me an email to my ETH mail that I think you can see over here. Or here, so c.cenedese, so my surname at eth.ch. Or you can reach me out on elements for the ones that are over there, or in whatever way you want. So thanks a lot for this opportunity to everybody.
Thank you. Thank you very much. Good luck for the next steps. Thank you all for participating. See you all to the next Autonomy Talk. Bye-bye.
Thank you.
Bye.